Well, it looks like it's time to start. Welcome back, everyone who's going to watch this video later on down the road. For the last review we'll do today on Thursday, I just have several quick announcements. We're on exercise 19 of the sample final exam that we're going to be going through out of 32 problems. So we're well poised to potentially finish this entire sample exam. If there's any problems I don't get to at the very end, I'll make sure to upload the solutions to those probably sometime on Friday. Also, our last quiz number 12 is due today, but also if you still need some time finishing that, I can still accept it for full credit. The last day to turn in any quizzes that have gone past due or to do any homework in the Newton homework system is going to be on Monday, December 15th. And just another reminder, I sent out an announcement in Canvas about this as well. If you haven't scheduled your final exam, please do so as soon as possible. If you're not sure where the link is to schedule it, I sent out a Canvas message in the inbox system here, which sends a message also to your ISU email, but you can also just send me a quick email and I'll get back to you right away with that link. The final exam has to be scheduled 2 p.m. or later on Monday or on Tuesday, December 16th, as per a math department policy. So just on those 2 days. Also, it's open note card. You can have as large of a note card as a 4-inch by 6-inch note card containing formulas and definitions. It contains full solutions to examples, and the note card will be collected after the exam. Well, let's go through the sample exam. This will be our last lecture for the semester, so congratulations on getting through the entire course. And here's where we left off. Problem number 19, it just says to graph this equation, 2x minus 6y equals 12. There's lots of ways to do this. We could say solve for the variable y, get it into slope-intercept form. But I think just as quick on this problem is, let's go for x and y intercepts. For the x-intercept, this will be an ordered pair where the y-coordinate is set to 0. So where the equation is, it'll turn into a 2x. My 6 times 0 is 12. This would mean x is equal to 6. We just divide both sides by 2. This term cancels out. And so if we have an x-intercept at 6, that's 1 point on the graph. We just need 2 points for the full graph. So now we'll go for the y-intercept. Y-intercept is another ordered pair, but this time the coordinate x goes to 0. Which means we're plugging a 0 way up here. So we'll have 2 times 0 by 6 times y is 12. And that's another really fast equation. We just divide by -6 and y becomes -2. So go down to -2 on the y-axis. And this whole line is our graph. We're doing it freehand, so it might look a little bent. Let's see if we can fix that a bit. And you might miss a point, but you can just make the point look a little bit bigger to cover up the margin of error there. So it doesn't have to be a perfect graph, but if I can tell where your point is here and here, then that'll do the job. Let's go on next to solving inequalities. These were some tricky problems that we did on the first week of class. So I think just to help out with the notes here, let's add some formulas that can help out with this particular kind of problem. So this is a problem all the way back in chapter 2. And let's see, I believe this was absolute value inequalities, section 2.7, part 2. And pretty much this is the guide to how to start off any problem that looks like one of these, or even the equality problem. Let's just drop it in. So now that we know what kind of inequality we're dealing with, it's a less than situation. When it comes to a less than, we take our absolute value inequality and split it into this triple-sided inequality. So watch out for this part right here, because it tells you exactly how it's going to start out. If it was a greater than, we would have had x less than -a or x greater than +a. But notice the common feature of both of these. You need the absolute value portion totally isolated before we even get started. So really the first step on this is to subtract 5. Then 6 minus 2x in absolute value is going to be less than 6. Now we can split this into a triple-sided inequality. -6 is less than 6 minus 2x, which is less than +6. We drop absolute value in the middle, and the a here, notice it turns into a negative version, so that's why there's a -6. Positive version on this end, so just +6. Now we're just going to solve this as we see it. The steps we would take is to subtract 6 from all three sides. That gives us -12 less than -2x less than 0. The next step is to divide by -2, which means we need to be cautious. This is going to change the directionality of the inequality signs. So if we take this side, divide by -2, the middle, divide by -2, and the far right side, divide by -2, the change is this inequality is now a greater than, and same for the 1 over here. So everything's flipped around. Simplifying this down further, we have +6 greater than x greater than 0. And to me, this kind of looks weird with the larger value on the left, the smaller value on the right. Usually anytime, say, we're doing inequality form or interval notation, we usually like the larger number on the right. So we can turn this around, go 0 less x less 6, and it's the same exact inequality. Just make sure it's opening towards the +6 here and pointing towards the 0 so that it's really the same inequality we're looking into. At this stage, we're home free. We just take those two values, excuse me, 0 and 6. Because this is strictly a less than inequality, there's an open circle here and here to convey 0 and 6 aren't solutions. But we shade then in the middle like this to convey every single number between 0 and 6 is a solution. In interval notation, we write it out as 0, 6, which is essentially the whole graph, except the entire number line turns into a comma, essentially. So just paraphrasing the graph. We did it, folks. We have the algebraic notation, we have the graph, and we have the interval notation. So again, watch out for the direction. If this was a greater than, we'd have split up the equation differently, and the number line would have had two different branches. So we would have had something like, say, -infinity to 0, 6 to infinity, changing around that direction. Well, let's go off to the next one. This one gets into some geometry. It says the hypotenuse of a right triangle. So first thing I would do for this one is just draw some generic looking right triangle to organize all this information. Okay, so there it is. We're told the hypotenuse of a right triangle is 3 times the length of one of its legs. So if this is the shorter leg, then the hypotenuse, the longest line segment, would be this one, 3 times x. The length of the other leg, we're told, is 128 feet. We want to find the lengths of the leg, the unknown length here, and the hypotenuse, 3 times x. Really, once we solve for x, the hypotenuse 3 times x is just going to be a really fast operation. So the major idea for this problem is it's really just Pythagorean's identity, or rather called Pythagorean's theorem. We'll label this side as A. Let me try again. Usually you want to keep one leg as A, the other leg as B, and the hypotenuse should be the one labeled as C, based on the way we usually write down that formula. So then Pythagorean's theorem, which is valid in this problem because it's a right triangle, which conveys a 90-degree measurement, that's right here at the corner, gives us Pythagorean's theorem, and it allows us to say C squared is going to be equal to A squared plus B squared. all we have to do is drop in what the A, B, and C is in this triangle into the formula. The portion that's all alone and squared is the hypotenuse. So that's why it's a good idea to call this one C. So this is saying take 3x, square it, set it equal to a squared, which is just 128 squared, so large quantity there, plus b squared will give us an x squared. And okay, remember the calculator, that's going to be helpful in just a moment. 128 squared comes out as 16,384 plus x squared. Left-hand side, we have to use properties of exponents. The 3 gets squared as well, or a 9x squared. Now we can subtract x squared from both sides. 8x squared equals 16,384. And you could get 0 on one side and start to factor. In fact, you could use, say, the quadratic formula if you really want to. But if you can isolate x squared, we'll just use the square root property on this one, fastest way to get through it. So that means we should take 16,384, this term, divided by 8. That gives us 2,048 after we divide. So x squared is 2,048. Let's double check that number. Okay, and that means then square root property implies x is going to be positive or negative square root 2,048. I put in the plus minus just as a reminder that if this was just a generic math problem, an equation that we were solving with no context like this, then we would have needed both a positive and negative solution. The x in this diagram has to be a positive quantity. So when we go to take the root, we're only going to take the positive solution for x. So here's our conclusion so far. X, we're told to round to 2 decimal places, so let's do that in the calculator. It'll be the square root of 2,048. And to 2 decimal places, that'll be 45.25. So we found the length of one of the legs. We just need the hypotenuse. The hypotenuse length is 3 times x, which means it's 3 times 45.25. And so this part is just a formality. Really, the major algebra was completed once we solved for x. So 45.25 times 3 gives us 135.75. These have units, so this is in feet. And let's put this in units as well. 45.25 feet going vertically. So we got it, folks. Pretty generic right triangle type of situation. Sometimes the equations we get can be involved. You might have had to use the quadratic formula, maybe complete the square on this one. But if there is just an x squared term, this is the preferred strategy. Get x alone, then just use the square root method. Well, let's move on to the next one. Here we're looking into exponent laws. Let's zoom in on this so we can see those fractions a little bit better. So that's x to the power of 1/3, 6 times x to the power -1, y power -3, y power +3 in the denominator, all to power -2. One really good strategy with this kind of stuff is kind of just divide and conquer. If you can simplify on the inside, this whole problem is way easier. So that's a good start. And by dividing and conquering, what I mean is, let's just focus on the like bases first. If you can simplify x to the power 1/3 over x to the power -1, then this whole problem becomes massively easier. And this is not too bad to simplify. You can take the negative power, bump it up to the numerator, and now the power is +1. Then least common denominator between these fractions is 3, so you can rewrite this as x power 1/3 times x power, the 1 becomes 3/3, multiplying like bases just adds up the exponents. So this becomes x to the power 4/3, and it'll stay in the numerator. So this already helps us out a lot. Same strategy with base y. We have like bases, and if we divide and conquer, we're just looking at y power -3 over y power +3. And this one goes different. We're going to send this base in the numerator down below to force the exponent positive. So it's 1 over the y cubed that was already there. Then the y cubed by the red dot gets demoted down to the denominator, exponent becomes positive. Just like with x above, we have a base times a base. We just add up the exponents. So this will be y power 6. Because it's in the denominator, when we plug it back in, we'll just leave it in the bottom. That means we can move forward on this. This is now equal to, first notice we didn't do anything with the 6. It's just right there, just like it was. But x's, once we simplify those bases, ended up in the numerator to a power 4/3. For base y, when we simplified that, it ends up in the denominator as a power 6. Now this problem is way easier to get through. We want to answer with just positive exponents. So the next offender is that power -2, but it turns into a power of +2. And all we have to do is flip the fraction on the inside, take the reciprocal. So 6 y power 6, x power 4/3 is what we'll get. Now this is a good time to start distributing the power. Every factor here, both numerator and denominator, gets raised to power 2. So this turns into a 6². So now it's 36. Y power 6² is a multiplication of exponents. That turns into y power 12. Likewise, we multiply the exponents here. This is just 4/3 times 2 for the new exponent. So it's x to the power 8/3. And we did it. I think this is about the cleanest way to do these kind of problems. I've noticed when grading exams, if we distribute the power -2 in just as we see it, almost universally, that became a really tough problem for people. So simplify on the inside first, and these problems become a lot more manageable. There's just less stuff to do right here, less stuff to do here once you're raising everything to a power +2, versus this had 2 factors in the numerator, 3 factors in the denominator. You're changing 5 factors with a negative exponent, or potentially a positive one. It's just way more work to simplify. Well, let's go off to the next one. Looks like what's up next is factoring polynomials. We haven't done too much of that just yet, so it's finally coming up in the notes. It says completely factor this polynomial. Looks kind of awkward. Power 3 sometimes doesn't look like the friendliest thing to deal with. But notice there's a greatest common factor. X is in all 3 terms, so you can just factor x out of this. Between 9, 24, and 16, I can't factor out of anything beyond just an x. But anything you can grab as a greatest common factor is always well worth the effort. So factor out x, it just means divide everything by x. It's exponent laws really at this stage. Power drops by 1 for a 9x² minus 24xy. Here, this becomes x power 0 really, or just 16y². And now this becomes just a lot more easier to start factoring. Next thing you might have noticed when you take a really close look at this is trial and error is probably a good idea. That's because 9 is a perfect square, and that strongly suggests try a 3x and a 3x to split up the 9. Next, a positive here says same signs. Negative here says inner signs are not just the same, they're both negative. And this is also a perfect square. If you see a 16 times y², that strongly suggests try a 4y and a 4y. This is not guaranteed to be the answer. So for this kind of perfect square polynomial, it does need a check. So the check is to see if you can get to here, the middle term. Multiply the outer product, 3x times -4y, it's -12xy. Multiply the inner product, that's negative 12 xy again. This sums to negative 24 xy. And we hit our target, negative 24 xy. That tells us this is the answer. And the cleanest way to write it in is x times 3x minus 4y squared. So that's our big factoring problem. That one kind of bit the dust the moment we took out the greatest common factor. So watch out for special products like these: perfect square polynomials, difference of squares polynomials, sum of cubes, difference of cubes are all things we should be ready to go for. Probably good form is to put on the 4" by 6" note card as well. Well, next up on the list looks like a word problem to get through. In the no partial credit section of the final exam, a lot of these problems were just set up but do not solve. So the whole problem was, can you write out the equations? But this one we're going to solve in full algebraically once we get to the end. So let's see here. We have a chemist needs to mix a solution at 11% iodine with one that's at 47% iodine to come up with 800 liters of a mixture now at 22% pure iodine concentration. What our goal is to find the number of liters of the 11% solution needed for the mixture. So we're only just looking for one quantity on this one. Let's start separating these out. There's two different kinds of mixtures that we're using. A solution at 11% iodine. Let's call that X. X will be the amount of liters for the 11% iodine solution. The other solution is the 47% iodine. So let's call that one Y. Y is the amount of liters for the 47% iodine solution. We're trying to come up with 800 liters of a mixture at a 22% iodine concentration. There's a system of equations we then have to solve, but X and Y are both in terms of liters. So if we just take X plus Y, we automatically get the total amount of liters equation, 800 liters. We need two equations next, but this is where we start using the concentration of iodine in both of the mixtures. We're trying to get 800 liters at 22% iodine. The way we would do that is take X, which is the amount of liters, multiply it by the concentration, 0.11, as a decimal. That's the amount of pure iodine coming from the first mixture, X. Then do it again to find the amount of pure iodine coming from the second mixture, Y. We take its concentration as a decimal, 0.47, multiply by the number of liters, which is Y. And what we get is not 800 liters, we're getting just pure iodine out of this. So we take the 800 liters, but we multiply by the concentration we are going for, 0.22, and this is the right equation. You know, we've basically done this problem once already. The context was just different. The parallelism here is so striking that let's take a really quick look at it. So pause right here. And somewhere down the line, there's a pretty similar problem. This problem number 6 is almost the exactly same scenario. Here we're using a simple interest formula as opposed to mixing two different quantities. But notice how we solved both of these problems. Well, set up one problem, we're about to solve the other. Over here, we had two amounts invested at different interest rates, just like we had amounts of liters at different pure iodine concentration rates. we had a total amount invested, much like the total amount of liters, and that's this total equation. But we also had the fact that we are earning 7.25% interest, and so we had a total interest equation. We took the total amount of money multiplied by the interest earned, and took the amount in one account times the rate, the amount in another account times the rate. But you know, that's the same exact thing that we did right up here. We took the concentration we're going for, multiplied by the total liters. So 800 went here again with the 22%. We took the amount of liters in one batch, multiplied by its concentration, and same for the other batch. So we'll delete this for now, so it's not a huge distraction if you read through these notes again. But I just want to call out, we are basically doing the same thing. And any kind of pattern recognition you can find like that really helps out for these kind of problems. It can stop a brain from panicking and thinking, this seems abstract, it's kind of crazy. You can kind of just remind yourself, wait, I've done this before. I just need to follow my nose on what I did for the other related problem. The only thing that's different here is we're solving this one. Lots of ways to solve this, but because there's decimal numbers over here, I feel like the elimination method is a little touchy. Let's solve for a variable, maybe say the variable x, and use the substitution method. We solve for x, we'll get x is equal to 800 minus y, and we take this whole thing and drop it right here where x is. That'll give us a new equation, 0.11 times 800 minus y. Just use an arrow to convey that substitution, plus 0.47y equals, don't forget the calculator, here's another one we need, 0.22 times 800 is 176, which means 176 liters of pure iodine. Next, 0.11 times 800 comes out as 88. So when we multiply here to here, we have 88 minus 0.11y plus 0.47y equals 176. So combining the like terms on the left, we have altogether 0.36y. We're also going to subtract 88 from both sides. So 176 minus 88 gives us 88. Divide by 0.36. And let's see what we're rounding to on this one. To the nearest liter. So this comes out as 244 liters with that level of rounding. And if I thought about our goal, find the number of liters in the 11% solution, which is x, I might have done this one a little bit differently. Maybe we should have solved for y on this one, then we would have had a solution for x. But you know, if we did it backwards like this, it's also not big of a deal because we can just put in that y value there. And now we have x as well. X is going to be 800 liters minus the 244 liters we just found. So now we have both the value for x and y in terms of liters. So go 800 minus 244 to get 556 liters. Well, we did it, folks. We wanted 800 liters at a concentration 22% iodine. So that means we had to double the concentration of the 11% solution, but we're doubling that concentration with another solution that's almost 50% iodine. That's why we didn't use too much of the super concentrated solution at nearly 50%. We used mostly the more watered down solution at 11%, 556 liters. And it's more than just a splash, it's a good chunk, but less than half for the more concentrated one to get to that 22%. Well, that's how these kind of questions go. Now we did one that's fully solved for the first time on this review. Let's go into the next one. This one's kind of all over the place. We went from a question that was way back in chapter 4, systems of equations, on that last one we solved. Now we're going to chapter 11, dealing with circles. It asks us to find the equation of this circle in standard form. Really, all we're doing is completing the square twice. So go to start out, x squared plus 8x plus, and before you write in y squared, this is mainly about organization at the moment. So we'll put in a placeholder for later. Go plus y squared minus 2y plus, then another placeholder. We want the constant on the right, but that was already done for us, which is nice. We're adding two values, so add something twice with space. Then the formulas we use go like this. We take negative b over 2 squared. This will be for the x variable first. The b coefficient is 8. Excuse me, it's just b over 2 squared. Not sure where my negative sign came from. Take just b over 2 squared. So this will be 8 over 2 squared, or 4 squared, which is 16. So 16 will go here and here. Then do it again for the y coefficient. B over 2 squared on this one will be negative 2 for b over 2 squared, which means it's a negative 1 squared for just a positive 1. So we're adding 1 both here and here. This generates two perfect square polynomials. So this one factors instantly as x plus 4 squared. So the sign plus to plus match up. We use this value right here, the same 4, or we can visualize it as take the square root of the 16 to get that 4 there. Same with y variable. Y goes here, minus sign copies down. Take the square root of this value, which is just a 1, and raise it to power 2. Or in other words, this negative 1 always matches that term with the same sign right before you squared it. Then on the right-hand side, we have 48 plus 16, which comes out as a 64. And this is kind of an odd question because it's done right at this step. They didn't ask anything further. But you know, because it's a review and just in case it's asked, let's also do a little bit more. Let's go beyond. Once we get to the standard form, which is right here, the center of this circle is going to be as an ordered pair, opposite of that coefficient, negative 4, and the opposite of that coefficient, positive 1. The radius, which we often call r, is going to be the square root of the constant on the right-hand side. So the radius is 8 for this particular circle. Now we did it. We have the circle in standard form where the red dot is, and just in case this is a question that's asked, we also now know the center and radius from this standard form right above. Well, now looks like we're going back to, say, chapter 3, dealing with graphs of lines, linear equations. It says to consider the line that goes to the point 2, negative 9. Let me copy it down here. It's to be perpendicular to a different line, y equals negative 3x plus 7. Perpendicular gives us a slope. We change the slope of the given line. We want to give the slope-intercept equation for the perpendicular line, the line that goes through 2, negative 9, and is also perpendicular to this line. But being perpendicular just tells us right out of the gate what the slope is. The slope m is the negative reciprocal. So we change the sign. It's now positive 3. We take its reciprocal, so it's 1/3. And this is what gives us perpendicularity. So now we have perpendicular slope. If it said parallel instead, we'd have done something totally different. If we wanted the parallel line, we'd have just captured that same exact slope and copied it down as negative 3. So the reminder is perpendicular, take negative reciprocal. For parallel lines, keep the slope exactly as is. Now we're building an equation this time. So the point slope form for the equation of a line is a great one for equation building. It goes y minus y1 as a slope m times x minus x1. We already know the slope, but we know x1, y1 as well. It was provided immediately in this problem. So x1 is a 2 in this problem. Y1 is a -9, which means we need to watch out for double negation. Substituting in those values, this is y minus -9 equals a slope of 1/3. So we have some fraction arithmetic to navigate through, times x minus 2. So let's work this through. This is going to be y plus 9 equals 1/3 x minus 2/3. We're subtracting 9, which means we're taking -2/3 minus 9, which means we need to do a spot of fraction arithmetic here. So this is -2/3 minus 27/3 for -29/3. So the equation in slope-intercept form is y equals 1/3 x minus 29/3. That's the equation of the line we were going for. Well, let's try out the next question then. This is kind of jumping around all over the place. The next one is an equation solving problem, but because the square root comes up, this is the last section of chapter 8, roots and radicals. Actually, this one's not too bad. Let's hide the word problem below. When it comes to solving these kinds of equations, the idea is we want to eliminate the radical. So first thing we can do is square both sides. That eliminates the square root from the problem. So 5 root x, raise it to power 2, equals x minus 6 raised to power 2. You might wonder why I didn't divide by 5. I think the algebra is a lot nicer in this format. It's not too bad to square both 5 and the root x. If I divide by 5 first, it does get a little irritating when you're suddenly solving an equation with a fraction. We'll get the same results either way, but I think this is the more straightforward approach. We have to square 5 to get a 25. You also have to square the root x, but that just gives us an x. X minus 6 squared does FOIL out. This is really x minus 6 times x minus 6. So the equation becomes 25x equals x squared minus 12x plus 36. And we're just about there. Subtract 25x from both sides. 0 is x squared minus 37x plus 36. Now we want to factor this thing. The quadratic formula will work on this. But there's a pattern you might have noticed with some factoring problems. If these are off by 1, this is very solvable just by factoring using the trial and error approach. I think you'll like how this goes. We'll go x and x. Both signs are negative. And if you go 36 and 1, that does the job. -36 times -1 is positive 36. They add up to a -37. And so the whole thing is complete at this step. So now we are using the zero product property that says x minus 36 is 0 or x minus 1 is 0. That's a step that's okay to skip, I would say, because you can also just eyeball the solutions. You get a 0 if you plug a 36 here, or you solve for x if you add 36 here. Likewise, add 1 here, and you get the next solution, positive 1. Or from here, you can just read it off, plug 1 inside there, and you get 0 times this quantity, which is still 0, balancing the equation. Well, this looks all well and good, but you can never celebrate too early when it comes to rational equations nor square root equations, because the issues with these things is that they have excluded values. So once we find solutions, we have to do some scratch work. So here's the check. First, take 36, plug it back into the original equation before you squared anything. You get 5 root 36 equals 36 minus 6. Square root of 36 is 6, so this becomes 5 times 6 equals 30. And that's a true statement. 5 times 6 is 30, so it tells us 36 is a solution. We don't have to do anything here. But we keep on checking. Forgot to say which one we're checking. Let me write in x is 36. Now for the next check, x is positive 1. Plug 1 inside here. We get 5 root 1 equals 1 minus 6. Square root of 1 is 1, so this just becomes 5 times 1 for a 5 equals negative 5. It was so close to being right, but this equation's false. How'd this come up? Well, when you raise this to the power 2, that negative 5 became a positive 25 squared. That's how this extraneous solution of x equals 1 emerges. It's just a side effect from raising this to a power 2 to solve the underlying equation. But the punchline is, that's not a solution, and we have to convey it somehow. So let's write out x equals 36 is the solution. Anything can happen in this kind of configuration. There could have been 2 solutions, exactly 1 solution like this case, or no solutions at all. Let's move on to the next one. Looks like the next word problem for the day. I think this is the last one to get through. It's a work problem, which makes this one a little bit more tricky. This question was pretty tricky on the last exam. So let's go back to the notes for from when this came up. This came up all the way back in, let's see, Applications with Systems of Linear Equations, section 4.2. And then it came back up again in chapter 7 when we were looking into rational equations. What we need is a good formula to kind of organize our thoughts to see how to put something like this together. And let's see if I can find it. You know, maybe it wasn't in this section at all. Let me look into the next section, 4.3. Could have swore it was that one. But you know, it's been a while since we've done these problems. So the next section, let's see. We have the simple interest formula. You know, maybe it wasn't in this section at all. Let's keep on looking. Must have been chapter 7, solving applications with rational functions is the first time this came up then. Okay, let's scroll through this again. Uniform motion came up. And here it is, the rate of work problem. So this is what I was going for. Took me a moment to actually find this in my own notes. So it's been a while. This was in chapter 7, not as long as I thought it was. But to really get through this question, the fundamental idea is that rates add together. Whether they're rates of work, rates of speed of someone riding a bicycle, driving a car, anything like that, we can have rates adding together or fighting each other. So if A is the time it takes from one person to do a particular job, whatever it is, B is the rate of time or amount of time it takes another person to do the same job, then 1 over A is a rate of speed, how fast you do one job for a unit of time, and so is 1 over B. If you add these rates together, it means both people are working together, and C is the time it takes to finish a job when they're both working together, gives us this summed together rate. So if we use this idea together in this new problem, we have information about working together. Fred and Tom can clean the garage in 53 minutes. So that's them working together. But working alone, we're told Tom takes 9 minutes longer to clean the garage than Fred would take working alone. So let's say, starting with variables, F is going to be time it takes Fred I'll just say briefly to clean. Working alone. There's also, let's see here. I color coded that in a weird way. So F is for Fred. Let's see if we can fix this. And T is for Tom. T is going to be equal to the time. it takes Tom to clean working alone. The question then is, how long will it take Fred to clean the garage by herself? It says that's kind of weird wording there. So we're solving for the variable f in this problem, and we can just set it up in this kind of way. We have all the things that we need. So go 1 over f plus 1 over t equals 1 over 53. So this is the actual equation we would have to solve. Again, this one came out to be really pretty tricky on the last exam 3. So this is a good one to really study to see just how it goes together. But we also need a system of equations. This is 2 variables in 1 equation. So I need another equation to move forward. But that's what this line is all about. We were told here on this line that Tom takes 19 minutes longer. So amount of time for Tom is 19 minutes longer to clean the garage than Fred. So T equals F plus 19. So we can substitute that in for T right here and solve this system. So it becomes 1 over F plus 1 over F plus 19 equals 1 over 53. So that's the equation we would like to solve. At this stage, it's really just a generic equation in chapter 7, solving a rational function. First thing we'd be worried about is excluded values, kind of like the excluded value 1 on the last equation. Here, f cannot equal 0, and it cannot equal negative 19. But when you think about it, none of those values make sense because f is the time it takes to do a physical action, clean the garage. So 0 means you didn't do anything at all, and negative 19 sounds like time travel, so we're just eliminating things that are just unreasonable in the whole problem as well. The next strategy in solving a chapter 7 equation is using the least common denominator. For this configuration, everything's fully factored, so the least common denominator would just be 53 times f plus 19. This is the smallest quantity we can put in all 3 numerators in order to cancel out the denominators. Let's write this in as another step so we're not cramming it in on the step above. 53f, f plus 19, divide by f, plus 53f, f plus 19 divided by f plus 19 equals, one more time, 53f, f plus 19 divided by 53. Takes a long time to write in this line, but this is more about organization. If you can cancel these things mentally in your mind, then that's great. But if you want to be extra careful, you can visually check your work as you go. So here, f cancels in that denominator. F plus 19 cancels. And on this one, 53 cancels. For me, this is the only way to be really sure I'm going to do this without mistakes. I think it's pretty iffy if I just try to do that all in my head. So sometimes writing a bunch of stuff is a great strategy just for the sake of organization and accuracy. We're left with a new equation, 53 f plus 19 plus 53f equals f times f plus 19. And it's kind of a beast of an equation. Once we solve for f, the whole work is done. We're just asked how long it would take Fred to clean the garage working alone. So now it's kind of like just an abstract algebra problem. We can solve this by first expanding things out. I'm going to need to know 19 times 53 out of nowhere. 53 times 19 is 1,007. So distributing here, we have 53f plus 1,007 plus 53f again, distribute again to get f squared plus 19f This one, I don't think I'm going to be able to factor it too nicely this time because the number 1007 is just beyond what I would even want to deal with. And it might not even factor nicely using ordinary integers. This one looks like a very good quadratic formula kind of problem. So let's simplify a little bit further. On the left, I've noticed a typo. That was a 7, should have been an F there. So combining those, we have 106F plus 1007 is F squared plus 19F. Let's go for a 0 on the left for this equation. 0 is F squared. We're taking 106 minus 19. Or rather, let's try this again. 19 minus 106 for negative 87 Fs. When we subtract 106F from both sides, subtract 1007 for both sides, and this is the equation we would like to solve. It's now the quadratic formula, so we'll say the solution to this by that formula is negative b plus or minus square root b squared minus 4ac divided by 2a. So let's identify the coefficients next. Leading coefficient is a on this one, and a is 1. Next coefficient b is negative 87, and the constant term, the last coefficient, is negative 1007. From that information there, we can solve for the discriminant, b squared minus 4ac. b squared minus 4ac is going to turn into negative 87 squared minus 4 times 1 times negative 1007. So pretty big number on this one, it looks like. So negative 87 squared minus 4 times 1 times negative 1007 gives us this figure, 11,597. So that's a large discriminant. But you know it's positive, so that tells us there's going to be 2 real number solutions to this equation. A little bit of a concern because we're expecting one answer to this. So one of those solutions is likely to be eliminated. I already forgot the number. Let me double check. 11,597. So that quantity is the discriminant. We can now substitute it in. Kind of getting short on space, so let's continue to the next page. F is now negative b, so that's going to be negative of negative 87 for a positive 87, plus or minus the square root of 11,597 divided by 2 times a, which in this problem is just a 2 times 1, so just a 2. Now we can calculate these. Let's see what f comes out as. In your calculator, make sure you take a parenthesis to capture the entire numerator. A7 minus square root, 11,597, divide by 2. So I used the solution with a negative sign first, and I've gotten a negative answer, negative 10.3. And I forget what the unit is on this. This is in minutes, and we're rounding to the nearest minute. We'll keep 1 decimal point for this step and then round on the further on the next step. So f is either equal to negative 10.3 minutes or f is equal to, let's change the sign. There's 2 solutions, so now go to positive on this one. And that would be 97.3 minutes. That sounds a little bit more reasonable. F is the time it's going to take to clean the garage. It can't be a negative time, so this is automatically eliminated. And this would be the answer to this entire word problem. Takes 97.3 minutes for Fred to clean that garage. Well, this one was kind of a tough looking problem. It didn't look like it'd be nasty from what we saw here. But once we went to clear the denominator, the polynomial equation we had to solve, this quadratic in f, was not the nicest, but also keep in mind, it didn't actually really matter how terrible the numbers got. Still, it's the same amount of steps to run this through the quadratic formula, put it in the calculator, get the values off. So don't let the size of the numbers intimidate you too much when you go to solve these kinds of equations. The quadratic formula really doesn't care how big they get. Well, here's our next one to try. This one is a system of equations. And we know we've already solved a system of equations using the substitution method several times, in fact. So just for the sake of variety, let's solve this one using elimination. Eliminating the variable x is not great. I need the least common multiple between 2 and 9. So I'd have to multiply row 1 by -9, multiply row 2 or equation 2 by -2, or excuse me, by +2, and that doesn't look too helpful. I think it might be easier to eliminate variable y. All we would have to do is multiply second equation by -9 to make that happen. So first let's copy in 2x plus 9y equals 28. We're going to multiply this whole equation, both sides, by -9. So multiply by -9. We'll get -81x minus 9y equals large number. Let's see what this one comes out as. So 32, rather -32, we're multiplying by -9. So it comes out as a positive 288. So equations look bad to start, but here's where it starts to clean up. Tally both the equations, so we get -79x equals, variable y is eliminated, and 28 plus 288 is going to give us 316 altogether. So take 316, divide by -79. That comes out as an even -4. And we're pretty much halfway there. We take this value, -4, it's half the answer. We're going for an ordered pair xy. And we can plug that into, say, this equation right up here. So we're still making a substitution when we do this, which is kind of funny. Even though it's called the elimination method, you still substitute somewhere. And here's our big substitution. X is -4, so you can put -4 in either equation. The top equation just happens to look like the nicer one. Plus 9y equals 28. So -8 plus 9y is 28. Add 8 to both sides, and 9y equals 37. Seems kind of weird all of a sudden. Let's keep on going. 37 divided by 9 gives us 37/9, and we have a value for y. So y comes out as 37/9, kind of random on this one. And that means the solution is xy equals -4, 37/9. Let me know if you can spot if my numbers went sideways on this one. 37/9 just seems kind of random out of nowhere. Double checking. You know, if you add 8 to 28, I believe you'll get a 36 on that one. Let me revise on this. And then 9 will go into 36. Let's see, we can divide 3 first. 3 goes into 36 21 times, goes into 9 3 times. Divide by 3, and 3 goes into 21. Or hang on, my arithmetic is kind of going sideways. It must be getting tired. You can divide 3 numerator and denominator on this one. 3 goes into 36 12 times. It goes into 9 3 times. I think we're getting back to track. And then 3 will finally go into 12 4 times. Okay, we finally got the value. So -4, +4. That looks better if we just slap it with a highlighter like before. This is not to say if you get some weird looking numbers, it's necessarily wrong. But oftentimes with these problems, we just expect some cleaner answers. So that was suspicious when I got a wild fraction looking at me on paper there. Well, let's go off now to the next few problems. Here we're getting towards the end of the review. We're going to solve a couple more inequality questions, and here's the first one to take a look into. And right out of the gate, this one's kind of a hard one. We had something like this on exam 3 as well. We need to have 0 on one side for our methods of solving this inequality to run smoothly. So really the first thing we should do is take 2x, x minus 7, and subtract 1. Then we can convert that into a fraction. It's really 1 over 1 you're subtracting. This is now less than or equal to 0. We can get the least common denominator in action here by just multiplying by x minus 7. X minus 7. And then there's just one denominator now, least common denominator. And this turns into 2x minus x minus 7 is less than or equal to 0. So this is our next opportunity to do a little bit of fraction arithmetic. Distribute the negative inside, and we get 2x minus x plus 7 over x minus 7 is less than or equal to 0. So finally, combining the like terms, we have x plus 7 over x minus 7 is less than or equal to 0. Now that means we're ready to start the method. First thing we do is we get cut points. Cut points are the values that make either the numerator 0 or the denominator 0. We could get a 0 on the numerator if x is -7, and we can get 0 on the denominator if x is a +7. But 0 on a denominator is always sketchy. Keep in mind, this positive 7 is going to be an excluded value in this problem. Now, once we have the cut points, we can plot them on a graph to organize all this information. Here's -7, +7. We have a less than or equals to. I know -7 is a solution. That will give us 0 is less than or equal to 0, so we can fill in that point. But +7 is not a solution. It's an excluded value in this problem, so we put an open circle on that one. But now the question becomes, where are the other solutions? And here's where we start to use test points. In this interval right here to the left of -7, we need to pick a convenient value for x. Let's go with -8. Plug it into the inequality in this form where we got less than or equal to 0, and we get -8 plus 7. -8 minus 7 equals -1 over -15. Negatives cancel, so that's greater than or equal to 0. So we get positive in that region. Next, pick something convenient in the middle. I would say 0 is awfully convenient. Plug that test point here, and it's just 7 over -7, which is negative. So in this entire region, it's only ever negative values. Then one more time, in this region, we can pick x equals 8, which means we're plugging 8 here. This will be 8 plus 7 over 8 minus 7. But that just becomes 15 overall. So we're bigger than 0 here, which means positive in this region. When it said less than or equal to 0, it meant we were going for this region where the negatives are. And so this is the entire solution set. Goes from -7 inclusive up to 7 excluding it. So in interval notation, the solution set is, start with a bracket rather, from -7 to +7 is that solution set. Well, we have the solution set in algebraic notation, that's this right here, and also in interval notation. We use the graph as a support to get down to here. Well, we're up to the penultimate problem now, solving another equation. Let's give this one a try. It's another equation back in chapter 7, and it's not in the most convenient form because that denominator should be factored. So let's start by rewriting this as 5 over x plus 3. Give a little bit of space in the numerator for that one. It's not a plus, it's a minus 2 over x minus 3 equals 2 over, and then factor this denominator. X squared minus 9 factors as a difference of squares pattern, x plus 3 times x minus 3. And this tells us a lot about the problem so far. The excluded values are that x cannot be negative 3, x cannot be positive 3. We already knew that from here and here, but when we factored, we also learned those are the only excluded values. Next thing we know is that the least common denominator is x plus 3 times x minus 3, and that's why we left a little bit of space. The strategy is now clear denominators using that. So multiply by x plus 3 times x minus 3 into all three numerators. It's tedious, but it's worth the effort and also gives your brain a bit of a break. It can kind of refresh itself or doing the mundane task of copying this all in. Now it's back to algebra. Cancel these. X minus 3 is over here, just wipe out. The entire x minus 3, x plus 3 just annihilates itself with that least common denominator. And so the whole set of survivors is now a new equation. 5 times x minus 3 minus 2 times x plus 3 is 2. It's been transformed into a linear equation. Next, we can distribute 5x minus 15 minus 2x minus 6 is positive 2. Combine our like terms, we have 3x minus 21 is 2. So add 21 to both sides. 3x is 23. Divide by 3. 23 is prime, so right at this step, x is 23/3. The whole problem is over. This is not an excluded value. We have the whole list up here to compare it against. So this is the unique solution to this problem here. Well, that takes us to the final exercise for the entire semester. Congratulations on getting to this point, folks. This one is solving a quadratic inequality and also graphing a parabola all in one. So we have parts A through F on this one. So 7 points. Looks like it's like 1 point per part. Part A first asks, does a parabola open upward or downward? And we can tell right away by that negative leading coefficient, because it's a -1 times x squared, it opens downward. I think this is a good way to answer the question on exam settings. Circling is a little bit faster to write down. For the axis of symmetry, this is where you're using the x coordinate for the vertex formula. Axis of symmetry is going to be x equals -b over 2a. The b coefficient is the 2 over here, so this becomes -2 over 2 times the a coefficient over here, which is a -1. So this is -2 divided by -2 for a +1. So the axis of symmetry is the equation x equals +1. Let's draw it lightly as a vertical line going through +1 on the x-axis. For the next part, it's asking what is the vertex? That's v equals, and you know what? We have half the information. The value 1 goes here. To get the other value, the value for y, here's what we do. Go back to this parabola. Y equals -x squared plus 2 times x plus 3. But in place of x, we put in the value for the x coordinate here of the vertex, or the value where we found for the axis of symmetry. So 1 goes in both of those spots, and y is now equal to -1 plus 2 plus 3, which gives us 4 altogether. So vertex is at 1, 4. So go up 1, go right 1, so you're on the axis of symmetry. Go to a height 4, and that's the vertex, the tallest point on the graph. Now we want all intercepts, so x-intercepts and y-intercepts. The y-intercept in this problem is always the freebie because the y variable is solved for up here on the top. Recall from what we saw earlier, a y-intercept always has 0 in for x. But when you plug in a 0, you'll get 0, 2 times 0, so still 0, plus 3. So it's just a total of 3 altogether. So that means that's another point on the graph. And that makes sense because the vertex here should be either the highest or the lowest point. For going downwards, it's the highest point, but we said it should be going downwards on part A. So that's some nice consistency so far. Next up is the x-intercepts, but that one's a bit of a process. For x-intercepts, and I don't know how many there are going to be, all I do know is you set the y variable to 0. So let's do this over here on the right, since it could be a good amount of algebra. 0 is negative x squared plus 2x plus 3. Maybe we can get away with factoring on this one. Let's multiply both sides by -1 to make factoring easier to visualize. 0 is positive x squared minus 2x minus 3. So now if we go to factor this with trial and error, it can go x and x minus 3 plus 1, and that does the job. These two values multiply to -3. They add to -2, so we have the right values. This tells us x is positive 3 or -1. Positive 3 causes 0 equals to 0 to balance, and so does -1 right here. So the x-intercepts, we're told to write them as ordered pairs, are going to be 3, 0, -1, 0. So let's plot those. 3 zeros here, -1 zeros here. Notice they're the same distance away from the axis of symmetry. Likewise, because we have an axis of symmetry, I also know there's a point here, and the graph of the whole parabola goes about like this. It's freehand, so it's not perfect, but that'll do the job. Well, we did it, folks. That's the graph. Last thing we're doing is solving the inequality, negative x squared plus 2x plus 3 is bigger than 0. But this is the graph of negative x squared plus 2x plus 3. So it's greater than 0 just whenever it's above the x-axis. So the solution set for this one, for wherever it's greater than 0, goes like this. It's -1, 3. Notice it says no work needed if using the graph in part E, and we definitely use that graph, but keep in mind the inequality is strictly bigger than 0, so that's why we have a parenthesis rather than a bracket. It's kind of confusing because we do have a solid dot here, but that was just meant to be a point on the graph, not a solid dot in the same sense that this is a solid dot, giving us a bracket in interval notation. But we did it, folks. This is the last problem for the review. I'll have this saved up and uploaded to Canvas. So as you're studying for the exam, keep in mind there's 3 different versions of study resources available here. There's also, in the Newton homework system, a different version you can look into, split into 2 parts. And as you're studying for the final exam over the weekend, don't hesitate to reach out. Whether you're turning in a quiz, Monday is going to be the last day to accept them, or just general questions on reviewing for the exam, I'll be happy to help out. But have a great night, everyone. Last thing to do is to get through the final exam, and we'll be completely done with the course. Congratulations on getting through.